Today I'm going to read how graded potentials can initiate an action potential from my biology textbook, Human Biology, 8th edition. Graded potentials can initiate an action potential. The resting potential of a neuron undergoes a slight change when an impulse arrives from another neuron. Depending on the type of signal and its strength, the change might be to depolarize the membrane, move the voltage closer to zero, or hyperpolarize it, make it even more negative. These transient local changes in resting potential are called graded potentials because they can vary in size. A key feature of graded potentials is that they can add up in space and time, meaning that many incoming signals from other neurons produce a bigger change in membrane potential than does one impulse alone. This is known as summation. If the sum of all graded potentials is sufficiently strong to reach a certain triggering membrane voltage called the threshold, an action potential results. An action potential is a sudden temporary reversal of the voltage difference across the cell membrane. Once an action potential is initiated, it sweeps rapidly down the axon at a constant amplitude and rate of speed until it reaches the axon terminals. Functionally, an action potential, also known as an electrical impulse, is the only form in which information is transmitted long distance by the nervous system. An action potential is like a single monotonic beep. An action potential is like a single monotonic beep in a touch-tone phone or a single on-off pulse of current. Its meaning is provided only by where it came from and where it goes, that is, by how the nervous system is wired. Action potentials occur because the axon membrane contains voltage-sensitive ion channels that open and close sequentially once threshold has been reached. An action potential occurs as a sequence of three events: depolarization, repolarization, and reestablishment of the resting potential. Depolarization: sodium moves into the axon. When threshold is exceeded, voltage-sensitive sodium ion channels in the axon's membrane open briefly, and sodium ions from interstitial fluid diffuse rapidly into the cytoplasm of the axon. This influx of positive ions causes depolarization, meaning that the membrane potential shifts from negative to positive. Repolarization: potassium moves out of the axon. After a short delay, the sodium ion channels close automatically, but the reversal of the membrane polarity triggers the opening of potassium ion channels. This allows more potassium ions than usual to diffuse rapidly out of the cytoplasm of the axon into surrounding interstitial fluid. The loss of positive ions from the cell leads to repolarization, meaning that the interior of the axon becomes negative again. Reestablishment of the resting potential. Because the potassium ion channels are slow to close, there is a brief overshoot of membrane voltage during which the interior of the axon is slightly hyperpolarized. Shortly after the potassium ion channels close, the resting potential is reestablished. At this point, the axon is prepared to receive another action potential. The entire sequence of 3 steps takes about 3 milliseconds. While an action potential is underway, an axon can't generate another action potential. This is because sodium channels only remain open for a short period of time, and once they close, they cannot be opened again until the membrane potential returns to its resting potential. The period when another action potential cannot be generated is called the absolute refractory period. The presence of an absolute refractory period ensures that action potentials always travel in one direction only, because an area of the axon that has just experienced an action potential cannot produce another one right away. The absolute refractory period is followed by a brief relative refractory period. During the relative refractory period, most of the potassium channels are still open and the membrane is slightly hyperpolarized, making it harder than usual to generate the next action potential. In practical terms, this means that by encroaching into the relative refractory period, very strong stimuli can generate more frequent action potentials than relatively weak stimuli can. The absolute and relative refractory periods are shown in figure 11.6. Whether or not a neuron is generating action potentials, the sodium-potassium pumps continue to maintain the normal concentrations of sodium and potassium ions and the normal resting potential. The actual number of sodium and potassium ions that diffuse across the membrane during a single action potential is so small compared to the activity of the sodium-potassium pumps that an axon can transmit many action potentials in a short period of time without adversely affecting the subsequent resting potential.